two ways in which we can change the fatty acid, which will therefore change the boiling point of that fatty acid and the retention time. So the two ways we can change a fatty acid, any fatty acid, is either to add carbons or double bonds. Right? And an important distinction, I'm just going to rewrite this real quick, is that double bonds for fatty acids are always cis. Do we remember cis-trans isomerism from OChem? Okay. This is actually a Z conformation, but that's okay. It's basically the same thing as cis. Okay. It means that there's, on this double bond of those two carbons, each carbon has a hydrogen and an R group, a carbon group. Cis means that the hydrogens are pointing in the same direction, or that the R groups are pointing in the same direction. And that's important because if this were trans, if the double bonds were trans, it has a huge impact on how these things can stack with similar molecules versus how these things can stack with similar molecules. And that has a big influence on the boiling. Okay, so first let's look at number of carbons. I'm just going to do little wavy lines for carbons. Okay, so if we have a solution of fatty acids, let's assume that we have a solution of just one fatty acid. That is, all fatty acids or fatty acid methyl esters have the same R group. Let's just assume. So those are the same number of carbons and hydrogens. These really big, huge, long hydrophobic side chains can have a whole bunch of little interactions. If you remember intermolecular forces, the weakest intermolecular force was London dispersion forces. And then there was dipole-dipoles, and then there was hydrogen bonding, and then ionic interactions. These London dispersion forces are really weak, but super numerous. They're really, 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 really numerous. And these, a whole bunch of carbons and hydrogens just has a lot of these London dispersion forces. So if I compare this fatty acid, it has a whole bunch of interactions in that side chain, and these can line up really, really well, pack really close, so we can have a whole bunch of fatty acids in a really small space interacting a lot with each other. Now what if I add two more carbons, or if I look at a different solution that has a single fatty acid that is 2 carbons longer than the previous one? So we'll just get more interactions, right? More London dispersion forces, meaning that the molecules are holding together more tightly. So if all we're comparing are, do you know what this means? I know people in my class saw this, but this means a fatty acid with 18 carbons, no double bonds. If we're comparing two fatty acids with the same number of double bonds, but different number of carbons, the one with more carbons is going to hold on to each other more, so the boiling point is going to go up. Right? Because in order to separate, or for something to go to the liquid phase to the gas phase, you have to pull all the molecules apart a little bit, so they aren't interacting as much, and so they can spread out. That's what a gas is. It's molecules that are really, really spread out from each other. In the liquid phase, they're a lot more attracted to each other, but they can still kind of flow. In the solid phase, they're really attracted to each other, and they're not going anywhere. That's all a phase change really is. Adding energy, pulling molecules apart, disrupting these intermolecular forces. So if we increase the number of carbons, we increase the boiling point. And we said if we, so we can say increase boiling point, increase retention time. So does anybody have the manual with that table of fatty acid retention times? You've got it. So does that agree with our conclusion here?
Yes.
Does increasing the number of carbons increase the retention time?
Yes.
Good. Does everybody follow that? Okay. More carbons means more interactions. Means it's harder to pull them apart and get them into the gas phase, which they're staying as a liquid on these little beads more, or for a longer period of time. So it takes them a longer time to get through the cone, which is what retention time actually is telling you, how long it takes to get through the cone. Okay, remember this rule, because this rule always works. When we're these rules are all else equal rules. By that I mean you can't change the number of double bonds and the number of carbons and make any conclusions. You can only change one. So all else equal, we're looking at fatty acid methyl esters. You increase the number of carbons, increase the boiling point, increase the retention time. Right? Okay. Double bonds. So if we look at, and this is where this being cis matters. Now, one of the big reasons that these have really high boiling points is that they can stack up on top of each other. Hydrophobic things love to stack on top of other hydrophobic things and stay together. That's a lot of the reason why DNA, that's really the big reason why DNA has a nice strict helical structure, double helix. Those bases like to stack on top of each other. These trans ones, do you see like a really similar structure between the trans double bond and this? Trans double bonds tend to have a lot higher boiling points than cis because these can still stack on top of each other really well. But when we put a little drastic change in direction of the chain, this fatty acid with this double bond, if it tried to interact with the same fatty acid with the same double bond, same spot, still cis, it just won't be able to stack on top of each other nearly as well. And I could draw this to make it look like it's still stacking on top of itself well, but that's not really in reality what it would be able to do. I think it's a door opening. It's got to be. So if we add a double bond, then there are far fewer interactions between two of the same fatty acids, or the interactions that are there are weaker. So if we're lowering the strength and quantity of interactions, then what's that going to do to the boiling point?
Lower.
So why would it be lower?
Because it's easier to break them apart.
Yeah, so if things aren't interacting as much and aren't interacting as strongly, it's easier to pull them apart. And easier to pull them apart really means it takes less energy to move them into the gas phase. So if we add carbon-carbon double bonds, we lower, we will lower the boiling point. Does that trend fit with that? Look at the 18.0, 18.1, and 18.2, and 18.3.
So the more double bonds you add, the lower the boiling point will be,
okay,
and the lower the retention time.
Okay. So 18.3, if we're looking at the fatty acids with 18 carbons and varying number of double bonds, we would expect 18.3 to have the lowest boiling point because there's the most number of double bonds. We would expect it to therefore have the lowest retention. Low boiling point means it's not spending very much time in the liquid phase, which means it's not on these beads, which means instead it's a gas and moving through the column. These two rules will always work. Know them, but don't memorize them. I mean, you know the difference between knowing something and memorizing it? If you memorize something, you're bound to mess it up and remember it incorrectly. But if you can justify why this is the case, then you should be able to reason through that no matter what, okay? But these are the two rules that will always work for fatty acid methyl esters. Okay? You will not be expected to compare those two and say which would have, like, just estimate which would have the higher retention time. Because if we compare these two, if we add carbons, then this would have a higher retention time. But if we add a double bond, then this would have a lower retention time. And there's no way to know which matters more. If you have your sheet, you can see, but as far as knowing that or being able to reason that, you can't do that. A lot of times in science or in chemistry especially, we don't try to figure out which of these has a lower retention time ahead of time. We do the experiment, look at the data, and justify the data based on the theory, or based on these rules. So I think 18.1 has a higher retention time. Is that right?
Yes.
So 18.1 has a higher retention time. So that tells us that number of carbons matters more than number of double bonds, at least for those two. But you won't be able to expect, or you won't be expected to estimate or rank retention times, unless it's really obvious. I mean, these you should be able to rank, because there is only one thing changing. But if two things are changing, then you can't determine.
Do you want us to justify those rules more, or the?
Yes. Well, or knowing, I mean, either you should be able to justify the rules, or if given a output, be able to, know something about the peaks, or be able to compare two peaks. If one peak has a higher retention time, what might that mean about the two fatty acids that are giving those two peaks? Either starting from the chromatogram, the output, or starting from these rules and justifying the rules. All right? Any questions on that? Okay, what's next? Can I erase all this?
Yeah. Taylor also asked for PI, will you give us the two pKa's, or will we have to pick the two? And if we do, how do we know which ones to pick?
How do we know which ones to pick? It's a tough question. I'd say there's two possibilities. So we're talking about the amino acid titration lab. There's two ways you could either be given the pKa data or have to find it yourself. You should definitely be able to interpret everything about a titration curve. That's really, really important. Okay, that's kind of the whole point of the lab, was making this titration curve. Remember, Y was pH, X was volume of NaOH, or equivalence of AOH, or moles of NaOH, whatever you made your graph as. And so you should be able to get the pKa's off of, or estimate at least the pKa's off of this. So how do we do that? Okay, so that's the equivalence points, right? Halfway up the vertical regions. And then, Dan, what'd you say next? Half the volume. Okay, so we have a certain amount of volume required to get to the equivalence point. We want half of that volume, and then what?
Goes over to your y-axis.
That's correct. Why is that the case?
Because pKa is pH at half titrated.
I mean, that's just saying the same thing in a different way. But why is that
when
the case?
it's like disassociated into like certain anions and?
Yes, but it's always it's
You
always.
have one protonated form and deprotonated form.
There is protonated form and deprotonated form all the way through this, but there's something very important or specific about that.
Equal number of moles of acid. No, wait,
Yeah, that's right. That's close. There's an equation that I know at least my people saw.
Henderson-Hasselbalch.
Yeah.
The same.
Did Brent talk about this equation at all?
Yeah,
The Henderson-Hasselbalch equation? I don't think I realized I don't think I put that on the study guide at all, but I did talk about, I'm pretty sure, knowing what the half equivalence points are and how you get pKa's from those. You won't need to use this equation, so don't worry about memorizing that, or certainly not plugging any numbers in. But these half equivalence points mean that so the equivalence point means that all of the acid has been converted into the conjugate base. That's what the equivalence point indicates. Okay, so however many moles of amino acid there is, you add exactly that many moles of sodium hydroxide to deprotonate all of one the acidic protons. So if full deprotonation occurs at the equivalence point, then half deprotonation occurs at half the equivalence point. And so at half the equivalence point, the concentration of A minus is equal to the concentration of HA. And so this ratio becomes 1. No matter what the concentrations are, that ratio is 1. The log of 1 is 0. pH equals pKa. You won't have to do that, that whole explanation. Not that you could do that on a multiple choice question.
So that first one.
This whole exam's gonna be multiple.
Whole thing, yeah.
Killer.
Whole thing.
So the first pKa will be the carboxylic acid proton on the amino acid, always.
We'll do that next. But so you asked knowing the PIs, right?
Yes.
So make sure you can do this, estimating pKa's off of a titration curve. Okay, however many equivalence points there are the same number of pKa's. All right. We might also give you the pKa's for a certain amino acid or peptide, whatever it might be. Probably we just did amino acids, so probably just amino acids. So either you should definitely be able to interpret a titration curve like this. For PI, the equation of PI is always the average of 2 pKa's. If there are only 2 pKa's for your amino acid, then it's easy. Right? Put them both in, divide by 2. There are 5 amino acids where there are more than 2 pKa's. Really, there's more than that, but there are 5 amino acids that are considered to be basic or acidic. They are the polar charged amino acids. I think that Dr. Dom broke them down: non-polar, polar uncharged, polar charged. There are 5 that are polar charged: aspartic acid, glutamic acid, histidine, lysine, arginine. Don't know the structures. You'll be given structures if you need them. Sorry? No. But just for your information, so those 2 are acidic, aspartic acid and glutamic acid, which means they have a carboxylic acid on their side chain. So they have another acidic proton on their side chain. And then the other 3 are basic. They have some kind of amine, whether it's a primary amine, secondary amine. Do you know what those words mean? Primary, secondary amine, doesn't matter. They have a nitrogen that can accept a proton. And so when they're in their fully protonated form, right, we make things really acidic down here at the beginning, which means we're always starting with the fully protonated form. So those basic ones will also have an extra proton to lose. So those 5 will have 3 equivalence points, which means they have 3 pKa's. How do we decide which 2 to use? This is not ever the average of 3 pKa's. Don't do that. Always 2. How do we know which 2?
Choose the 2 like groups. If you have
Okay, that's right.
If you have a basic amino acid, then you're going to use the pKa from the amino group on the alpha carbon, and then the pKa for the amine, the second amino. Whereas
So
in
what?
carboxylic acid, you do.
Break it down to retard
Let's
mode.
make sure everybody knows exactly
Yeah,
what
like you're gonna have to dumb it down.
No, that's fine. That's aspartic acid. Okay, when it's fully protonated, it looks like that. Is that all right? So what do you mean by like groups in this example?
Carboxylic acids. It would be the
Oh yeah. Okay, sorry. Yeah.
So
So the two
you said
carboxylic
choose the 2 like groups.
wouldn't it be the carboxylic
So in this
acid?
case, it's the carboxylic acids. And so this pKa is about 2, this is about 4, this is about 9. So your PI would be around 3 for this. Now, why do we choose the 2 like groups?
It depends on which age group you pull out first.
Well, we know the order that they're going to be removed, right? pKa tells you the order of acidity. Lower pKa means more acidic. So this one, then this one, and that. So the thing that matters is the ionic states of the various forms of the amino acid. So if I remove this proton, and that becomes an O minus. Well, let's go back to this first. What's the total charge, or the net charge?
1.
Plus 1. If we remove all of this proton,
It's 0.
this is 0. What's a net 0 ion called?
Zwitter ion.
Zwitter ion. Okay, what's the next one to get removed? This
That one. Then it would be an
So that's a minus 1 anion. And then
You take out that one.
this one.
Minus 2 anion.
The pKa to go between these is 2, 4,
And
9. Well, what we look at are the ones around the Zwitter ion. Always the ones around the Zwitter ion. Now, the rule that Dan said to choose the 2 common ones will always work, but it works because those are the 2 that will be around the Zwitter ion. So if you have 2 carboxylic acids, then you'll choose the 2 pKa's for those. But I wouldn't think about it in those terms. I would consider the various forms of the amino acid, the various ionic forms of the amino acid, find the Zwitter ion, and use the 2 pKa's around the Zwitter ion. That is the real way of determining which pKa's to use. Pi means the pH required to get almost very, very, very close to all of the amino acids to exist as the Zwitter ion. If we are halfway, remember that this here, this pKa of 2, means that we have half cation, half Zwitter ion, right? That's what pKa means, is we have half of each of those. Or the pH, when pH equals pKa, we have half of each of those. pH of 4, or pKa of 4, means we have half Zwitter ion, half minus 1 anion. If we're right in between those, which is what an average is, then we will have almost none of this, almost none of this, almost all Zwitter ion. All right? Find your Zwitter ion, the 2 pKa's around that.
If you were gonna ask us, you would give us the structure of the amino acid?
Yes, absolutely. Yeah, you will not be expected to remember the structures or to know exactly where things are going to get protonated. I don't think that's too easy to mess up, and then you have no chance from there of answering the question right. But it would be a good idea to remember that at low pH, carboxylic acids have protons, because low pH means there's lots of protons in solution. So if this had a negative charge, it would grab that proton and become neutral like this. There's lots of protons around. And also at low pH, basic side chains or this alpha amino group are also going to take the proton. And as you increase the pH, you remove some of those protons. And so you tend to go from positive charges, well, you always go from positive charges to negative charges on the amino acid itself. But you will be given a structure and any other information that you need in terms of what the molecule looks like. Okay, what was the other question that we were asking? Was it Andrea or did I answer it? The what, sorry?
Covered mine with that.
Okay.
So the last one that Taylor has.
Okay, sure.
Question 1 for experiment 5. So be able to describe how you would create a standard solution of riboflavin at a certain concentration using a more concentrated stock solution, a volumetric pipette, a volumetric flask, and sodium acetate buffer.
This applies to a lot more than just riboflavin. Riboflavin is just an example, but you should be able to describe how you would make a certain concentration of a solution. So what's the equation you're going to use?
C1V1 equals C2V2.
This is called the dilution formula. You might see it as M1 V1 equals M2 V2. That just means this concentration is specifically molarity, but doesn't really matter. Anyway, this says if I know the initial concentration, and I know the final concentration that I want, and I know the final volume that I want, then I can decide how much of this initial concentration to withdraw and then dilute. Okay, so we'll just do an example. We'll just do the example from the riboflavin lab, I guess. We had 20,000 nanograms per milliliter of riboflavin that was in that stock solution that was wrapped in foil and in the fridge for the most part. This looks really concentrated. 20,000 is a big number, but this is nanograms, which is a really small amount. So. And then the first dilution that you did, so this was the class stock solution. When you were making your standard solutions, you then diluted this first and made your own stock solution. By the way, you won't be expected to remember procedural steps and recreate them. You should have an idea about the procedure that you did, but you won't be asked to recreate the procedure. That's not worthwhile. Anyway, the first thing that you were supposed to do was to make your own stock solution of 200 nanograms per milliliter of riboflavin. So in the study guide, it says know how to make a standard solution from a more concentrated stock solution, a volumetric pipette, a volumetric flask, and buffer. So volumetric pipette was the draw as well at all. They were the things that very vaguely looked like this, that kind of had a little bit wider region in the front. Maybe this one said 10 milliliters, which means if you fill this up to 10 milliliter to the line right there, that was 10 milliliters, and you empty it all out. So, and then the volumetric flask, oh boy, was the flask with the flat bottom that had another line there that had a line up at the top, meaning that if this is a 100 milliliter volumetric flask, if you fill it up to the line, then that's 100 milliliters. So with just these, you should be able to make this concentrated stock solution. So how do I decide how to do this? Or if you were to describe the sequence of steps you would use to go from here to here using those, what would you do?
Well, what's your second volume going to be?
Well, let's say 100. Yeah, we'll say that. You're right. That would be a good thing to specify first. How much of it do we actually want to make? Because that is what V2 always is. V2 means final volume. It doesn't mean volume of this original stock solution that you're using, and it doesn't mean volume of buffer that you add to dilute it. It means everything together at the end. What's the final volume? So we'll say 100 milliliters. But that is the first thing you should determine. That absolutely is the right answer for the first step. How much of our final solution do we want to make? Let's say 100. What will we do next? Okay, so let's plug everything in here. So we would get, so we would say 20,000 times V1. We don't know V1, right?
Right.
We don't know how much of this concentration to use. We do know C2, that's our final concentration after the dilution. We do know V2. V2 is always final volume. For using a volumetric flask, which is a really good idea, then the final volume will always be the volume that the volumetric flask indicates. Volumetric flask, any one volumetric flask is only good for one volume. In this case, this one's good for 100. So this should be 1 milliliter. Okay, so what does this mean? Now we know V1 equals 1 milliliter. What does that mean? Because that's easy, right? Plugging the numbers into the equation is easy, but when you're describing the steps, you need to be a little careful about what you say here. So somebody tell me, what would we do next?
You use 1 milliliter of concentrated riboflavin.
Okay.
You put it in the volumetric flask, and then you raise the volume using the sodium acetate
Okay.
to 100.
Or whatever diluent you use.
So we draw 1 milliliter of our stock solution, or however much of the stock solution this equation says to draw. So 1 milliliter of this with, so there are lots of different sizes of these volumetric pipettes. You saw a bunch of them. Add that into here, and then add 99 milliliters of acetate buffer, right? Wrong.
Well, you added it.
You add it up to the line.
Yes, you add it up to the line. Do not measure 99 milliliters somewhere else and then add it to this. There is a load of error involved in any measurement. It doesn't make sense to measure it somewhere else and then add it if you can just add it to this. The point of a volumetric flask is that this line is 100 milliliters every time. Really, really, really close to 100 milliliters. So do not take a milliliter of this and add it to 99 milliliters of acetate buffer. Add the 1 milliliter here, fill it up to the line. So that would be the entire process. Determine how much of this original stock solution you use, add it to the volumetric flask, fill the volumetric flask up to the line, or dilute to volume is the terminology for that. Okay?
About Beer's Law.
Beer's Law? Sure. Okay, Beer was a real person. I don't know what his first name is, but it's sometimes called Beers-Lambert's Law, but yeah. Beer's Law works just fine. Beer's Law. Okay, so what is Beer's Law? Mathematically, what is Beer's
Big
Law?
A equals little a, b, c.
You might see that. They mean the same thing, essentially. Yeah. Well, the units on A and epsilon can change to suit your needs, and I'll tell you what those mean exactly. Sorry?
Which one will we?
All of them. So we're gonna go over that. So what's big A?
Absorptivity. Absorbance?
No, absorbance.
Yeah.
Yes.
I know.
Okay. So A is absorbance. Somebody define absorbance for me.
Ability to absorb light.
No, I wouldn't say that. I would say absorptivity is closer to that definition, little a.
Promotion of an electron from the lower to a higher.
Okay, yeah.
Yeah.
Let's dumb it down a little bit beyond that. You're kind of, sorry?
I say K, you share.
Okay, if we have a solution and it has some things in it that can absorb light at a certain wavelength. Let's say we're doing, I don't know, 400 nanometer light. Doesn't matter what it is. So we have a solution, it can absorb this light. So there will be some kind of incident radiation, some initial intensity of light. The instrument knows how much light it's putting in. These molecules absorb some of that light. A new intensity of light comes out that is less than or equal to I naught, cannot be greater than, because that means that you're getting more light out than you put in, which is nonsense. Okay. It converts the ratio of I to I naught using a log term into this absorbance. So really, absorbance is just how much light came out relative to how much light you put in. At one wavelength of light. There are three factors that can affect a molecule or a solution, rather a solution's ability to do that absorbance. So as this I goes down, this resultant intensity, as that goes down, absorbance goes up, right? Because if there's less light coming out, then more of it was absorbed. Okay. But you won't need to show that at all. But anyway, there are three factors that affect absorbance. They are these three. So what's little a? What's the name for little a?
Absorptivity.
Okay. And this is again one of those opportunities where they could have named things differently, but they didn't. I mean, because those are way too easy to confuse, absorbance and absorptivity. This is sometimes called molar absorptivity. Or this E, or epsilon, was called the extinction coefficient. They really all mean the same thing. The difference is the unit. The units are strange. Those are the units of that. If it's molar absorptivity, then it's on a per mole basis. If it's just absorptivity or extinction coefficient, it's on a gram basis. We like to do things in terms of moles because moles actually means how many particles are there. Grams just means how many protons and neutrons are there, which isn't necessarily as valuable, right? Because that's what mass really is, right? Just how many protons and neutrons are there. But if we know how many molecules are absorbing, that's a lot more valuable anyway. So absorptivity was what Dan's definition for absorbance, I think, better applies to. He said how well a molecule absorbs light. That's really what absorptivity is. So every molecule in the universe has a different molar absorptivity for a different wavelength of light. So riboflavin has a molar absorptivity at, oh gosh, what did we do? I think 365. No. I don't remember what it was. Maybe 285. I think it was 285. So I think that we did.
540.
I think that was the emission, not the excitation. Whatever, it doesn't really matter. But it has a molar absorptivity that's really, really strong or high at 285 nanometers, which means it absorbs this light really, really well. Other molecules might still absorb 285 nanometer light. They just don't do it as well, which means the absorptivity at that wavelength is low. So this means for the molecule itself, just looking at one molecule, how well does it absorb a certain wavelength of light? The better it absorbs that light, the more a solution is going to absorb that light. Remember, big A is on a solution scale. Little a is on a molecular scale. How well do the individual molecules absorb a wavelength of light? That's the big difference between big A and little a. Also, that big A is affected by these other two factors as well. But do keep those units in mind. They're really important. I mean, for absorptivity, I would not worry about the grams one. Just I would always consider it molar absorptivity. It's a lot more useful. All right, what is B?
Light path through sample.
How about the path length? I know that's what the manual says, or maybe how it defines it, but I know it's the same difference. But so path length, how did the path length manifest in this lab, or how did we determine it? Yeah, the cuvette. Almost all cuvettes and almost all instruments that use cuvettes use a square cylinder cuvette with a 1 centimeter length. So the path length in 99.99999 whatever percent cases is 1 centimeter. And really that's a lot for convenience, because if this number is 1, then it is irrelevant to this equation because it's always 1. Or at least we designed absorptivity. Notice this has centimeter in the unit. That's not an accident. Such that the path length doesn't affect the numerical calculation because it's always 1. So why would this affect absorbance? We look at these two different cuvettes, theoretical cuvettes. The second one we'll say is 3 centimeters long. Remember that light is passing through this sample. It's going to pass through this cuvette longer than it's going to pass through this cuvette. So just purely by virtue of having more time for the molecules to absorb, or more space, I guess space and time are kind of the same deal here. We can think of them as being the same. The more time or space that a molecule has to absorb before the light escapes, the higher absorbance is going to be. Notice absorbance is directly related to all three of these. As they all go up, absorbance goes up. Doesn't matter though, path length is always 1 centimeter, so know what it is. You won't ever have to use it because you're never going to see a 3 centimeter cuvette. All right, C. What is C? Concentration. Okay. This one is pretty apparent, I think. If we have this solution and we increase the amount of stuff in the same volume of solution, it's going to absorb more of that light, assuming it can absorb it in the first place. Okay, so if you increase the concentration, you increase the ability of that solution to absorb that light. Okay. All right. Is there anything else on there?
We go over the 5 graphs of the catalase lab, just because we never did ever get to the saturation point with the substrate, reaching the Vmax.
So you didn't see that at all?
No, it just kept increasing linearly.
Well, it will always keep increasing, but did it level off at all?
No, that's what I meant. It didn't have level
Because
off.
it always goes up, right? The rate never drops or goes to 0. The derivative of the rate goes to 0. Okay. So we have 5 different graphs from 4 different parameters that we can change. So we can change pH, concentration of enzyme, concentration of substrate, and temperature. All 4 of those have a profound effect on an enzyme's ability to catalyze a reaction, to turn substrate into product. All right, so 4 parameters, but 5 graphs. And you know what the 5th one is, it's a little weird. Well, this is the Michaelis-Menten plot. The Langmuir-Burke is the 5th one, but it comes from this data, these data. Okay, so let's start with, and remember rate is always on the y-axis, always. In this experiment, the way that we were quantifying the rate was in terms of the volume of oxygen evolving per time, per unit time. In this case, seconds, or if you did minutes, whichever, doesn't matter. And so we can define rates really as whatever we want it to be, as long as it's something per time. And O2 was a product that was easy to isolate. Right? We did a little copper wire that went up into the graduated cylinder, and as the reaction was going in the sidearm flask, and then the oxygen bubbled to the top and displaced the water, and then we could measure the volume of oxygen directly like that. Okay, and then the x-axis is what's changing. Those are these parameters over here. So what did the changing enzyme graph look like? You should be able to recognize all 4 of those graphs without the graph being labeled, of course. And you should be able to justify why the graphs look like they do on a molecular level. And when I say on a molecular level, once we get there, I'll tell you what I mean. But, well, we'll get there. What does this graph look like? When we change the enzyme concentration.
It goes up really fast and then plateaus.
What did you say?
It goes up really fast and then plateaus because you have.
It's just linear,
This one is linear forever. Why?
because the substrate is an excess substrate.
Now, there's an important caveat to this. And what did I tell you in my class?
Always assume that the substrate's limiting.
No, the substrate is never
No.
limiting. So I said, we said it was excess substrate. And excess is, that just means excess. So excess substrate or excess of any reagent means that there is way more of it than the other thing. So you will never run out of this, which means that your reaction will never be dependent on this. Dependent on how much of this is around. If you're not dependent on how much of this is around, then it's only dependent on the amount of enzyme. So and this line being linear, presumably forever, meaning it's never going to plateau, means there's always tons of substrate around to react with this enzyme. So if we add more enzyme, we get more reactions per second, which is what this is. We add more enzyme, we get more reactions per second. More enzyme, more reactions. This will never plateau if this is true. And you should have seen this for your trials, that this was pretty linear and did not appear to plateau at all, because there was always way more substrate on a per mole basis than there was enzyme.
Yeah, we
Okay.
never established that in our lab, so.
And I think it's implied, but not very clearly. So yeah, I understand that. I get that you wouldn't have gotten that. But, okay, so on a molecular level, so the post-lab questions, I don't know if Brent's class did this. I know he gave you other stuff to do, but the manual, as part of its post-lab question, says explain on a molecular level why these all look like they do. So on a molecular level, why is this linear forever? If it's linear, it means that you can always add more enzyme and get more rate. So on a molecular level, we add more enzyme, there are more things to do reactions. So, some of the people in my class were looking on a macro scale a lot, too much when they were talking about this. And if we want it on a molecular level, we want obviously to be on a molecular level. We want to know if you change these parameters, how does that affect each of these enzymes' ability to find substrate? If there are more enzymes, they are going to have a much easier time finding the substrate. Okay, so just focus in really as much as you can on how the enzyme is affected by all of these factors. If there's more enzyme, there's more reactions. That's an easier one to describe on a molecular level. Okay, is this all right for enzyme? How about substrate? What does the graph look like when we change substrate concentration? Okay. So this is the one that plateaus. This is Michaelis-Menten enzyme kinetics right here. Another important part of this, and if you remember, for any of these parameters, if you're changing one, the other three are constant. And that's, of course, an important thing. So the amount of enzyme, remember this graph was made with just 5 points, right? Each of those points had the same amount of enzyme. Each of these points represented a different trial. This was trial 1 with low substrate, more hydrogen peroxide, but those were one complete trial. You got a number, you plugged it into this graph. But each of those has constant enzyme concentration. So why on a molecular level does it plateau?
There's lots of enzymes to react with the substrate so that they react, but then there's not enough substrate. Or I mean, there's more substrate, not enough enzyme.
It is not a this is still excess substrate. So when this plateaus, it's not because of a lack of substrate. And remember, this is a complete trial. This isn't the end of one trial, right? This trial had a higher rate than this one, but the difference between those isn't so great. The benefit of going from this substrate concentration to this one wasn't that great.
Slower because the enzymes.
Still
The rate is
increasing,
not
but
slower,
I
right? Rate is the y-axis, and so if this is higher,
becomes more constant because the enzymes are less as a substrate.
I mean, the rate is constant for within each trial. Now between trials, though, I mean, you are right essentially, but the rate for this trial is the same for that trial at all points along that trial. Same for each of those. But the benefit of adding extra substrate to get to this point is not that great. Whereas when we went from here to here, that's looks like about, what, at least twice, 2.5 times maybe the rate. And it looks like the increase in substrate is about the same. I'm looking at those. So we get less and less benefit as we add more and more substrate. And we could do more of these. And this would appear to just really level off completely. So on a molecular level, and you were kind of, so a couple people were saying it. So what is significant about these points?
The enzyme is, all the active sites have been flooded with substrates. There's no more, you can't have any more reactions or anything. Nothing left. No
Okay.
spots available.
More enzyme, less reaction.
What is it?
More enzyme, less reaction.
No, and with the enzyme is constant. Remember, for all these trials, the amount of enzyme that's present is constant. So the key is enzymes have one active site, which means at any one snapshot in time, they can do one reaction. So if we have, remember this whole thing, enzyme plus product. So when enzyme finds substrate, we get this enzyme substrate complex that can turn that into product and release it. And then this enzyme is open up to get another substrate. At some point, there's so much substrate around that there is no downtime between this enzyme releasing product and finding a new substrate. If there's no downtime, then there's no delay in making another product molecule. And so if we double the amount of substrate, there's already no delay in finding another substrate molecule. So there's no benefit. Right? And if you double it again, there's still no delay. So it's about the time in between reactions. As we add more and more substrate, the time in between reactions gets so vanishingly small that it's not really a factor. So there's so much substrate that that this almost doesn't exist. Free enzyme almost doesn't exist. Okay? So on a molecular level, this is virtually not present because there's no delay between enzyme making product and getting a new substrate to make into product. Does that sound good? Okay, temperature.
This one is like a bell.
It'll increase the
So why does it start low? Let's start with that. So we actually had data that started around like 5 degrees, I think. So why does it start low? On a molecular level, again, why is the rate low when temperature is low? There's plenty of substrate and enzyme around. That's not a problem.
The molecular movement, the molecules aren't moving around.
Sure, well, that's kind of a truth of anything in life or in chemistry. There's not a lot of energy around, then not a lot of movement is happening. And any reaction, whether enzyme catalyzed or not, relies on there being enough energy to reach that transition state. Do we remember thermodynamics, any of that kind of stuff, right?
Yeah.
Right. So if we want to go from reactants to products, we have to have things colliding with enough energy or they won't change. Okay, so enzyme has to find substrate with enough energy to change the substrate into product. Low energy, there's virtually no reactions happening. There's a little bit, but virtually no reactions happening because we can't get up there. So on a molecular level, this is low at the beginning just because there's not enough energy. Molecules aren't moving around quickly enough with enough energy to do reactions. So why does it go up as we add more energy? That's basically the same explanation. The more energy there is, the more molecules are moving, faster they're moving, the more energetic collisions they have. Energetic collisions are what reactions really are. So we'll go up and 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 up. So what happens eventually?
It comes down.
So proteins don't like heat up to a certain point. the protein is not denatured down here. Please don't think that. Okay, the protein is just not moving very fast. But low heat does not denature proteins. This just means there's not enough energy to do reactions. But eventually, we will get a optimum temperature, and then sometime thereafter, it will drop to 0 pretty quickly. Okay, so some optimum temperature drops to 0. The protein enzyme denatures. When it denatures, denaturation means it loses its shape, right? It doesn't mean that its primary structure is gone, right? The sequence of amino acids is still there, but the quaternary, if applicable, structures or secondary and tertiary structures are gone, or at least disrupted to where the active site doesn't work. If the active site doesn't work, then the protein is no longer an enzyme. It's just a string of amino acids. The drop to 0 does not have to occur immediately after the optimum temperature. Sometimes it might, but by that I mean it doesn't have to go right up to the top and then go to 0. That wouldn't make any sense. That would be a very small window of optimization of the enzyme, right? So imagine if you got a fever and none of the enzymes in your blood worked anymore because you were ever so slightly above your normal body temperature. That wouldn't be good. Right? So yeah, we'll get a little bit of time at optimum and then back down to 0. Right, pH. Okay, it does look kind of similar to temperature in the sense that it starts low, goes up, and then goes back down to 0. But it is noted, or I think most of the data that we got didn't really support this, but it ought to look like a bell curve, vaguely like a normal. It's not a frequency, but it should kind of look normally distributed. You're familiar with that? So this means that there's some optimum pH at which this enzyme works, and if you move away from that pH in either direction, you decrease the rate. It doesn't have to be 7. In blood, it's probably close to 7. So catalase, the enzyme we're looking at, is a blood enzyme, mostly. So it's going to want to work really, really well at pH 7. Blood is a little bit more basic than that, but it's pretty close. But, stomach enzymes, where the pH is 1 or 2, those wouldn't work at all, right? So they're going to be optimized to work at a lower pH, or whatever the pH needs to be. Okay, so why does this happen? What does low pH mean in terms of the solution? Yeah, what is there a lot of in solution at low pH?
Hydrogens.
Protons, okay. Okay, so we can affect the ionic states of proteins significantly by changing pH. We saw, you were in my class, you saw basically exactly this before, but bear with me. So imagine that we have a protein. That's just the rest of the protein, and then there are 2 side chains just somewhere. Okay. At pH around 7, what's the ionic state of this going to be? Right, it's acidic. At low pH, this would have its proton. As we add more sodium hydroxide, or as we increase the pH, this is going to start to go away. So we would expect that to be negatively charged at around neutral pH. How about this amine group? Is it going to be neutral or positive? That is it going to look like this, or is it going to look like that? It depends on the amine, but most amines at pH 7 are going to have an extra proton. You don't need to know that. That's not a hard and fast rule by any But in any case, at pH 7, amines tend to be protonated and have a positive charge. Carboxylic acids tend to be deprotonated and have a negative charge. What do negative things and positive things do to each other? Attract, right? So they're going to pull each other close, and they're going to change the shape of the protein as a whole as they do that. Or if this protein or enzyme is optimized to work at pH 7, then the shape that it has, that is a result of these interactions, is the shape it needs to have to do the reaction, right? So it's the shape of the active site, the presence of the active site, is reliant on this interaction and thousands more. And if we can change how these charge groups are interacting, we can change the shape of the protein and have it just not work. So if, well, let's say we're at really basic or acidic pH, where there's lots of protons. So let's say pH 1. How is that going to change, if at all, this carboxylic acid? Right? A carboxylic acid, or the conjugate base of a carboxylic acid, there's lots of these around. It's going to want to grab one of those. And then how is this going to change? So this, I mean, just this amine or this ammonium ion now, this isn't going to change just because there's more protons around. It's already got its extra proton. So this is still going to be positive, but now there's no positive negative ionic interaction. So this is gone. The shape of the protein is going to change a little bit, but remember there's a whole bunch of different interactions of these side chains that are going to be affected by pH. So if you change 1,000 tiny interactions, then you change the shape of the protein significantly. And as you get closer and closer, or as you add more and more protons, that protein gets closer to being completely unable to do its reaction because you change the shape of the protein too much. Okay, we can go the other way. It's essentially the same argument though. So let's say we're at pH 12, which means there's a lot of hydroxide ions around. If there's lots of hydroxide ions around, then it'll take off one of those protons, but it'll also take off one of these. Again, there's no more ionic interaction. Change the shape, and the protein doesn't work. So if you move in either direction away from optimization, in this case 7, we're changing the ionic interactions between the amino acid residues of the protein. Don't ask me how that's a multiple choice question, because I have no idea. Okay, one more. Lineweaver break. Brent told me that he didn't go over this as much with his sections as I did with mine. So you're lucky I had to change one of the questions. How is Lineweaver-Burke related to one of the graphs that we've done already? So what on my x-axis, sorry?
1 over the substrate.
1 over, okay. So it uses the same set of data that you used for your substrate concentration graph, or the Michaelis-Menten. That's the one that plateaus. And then what's on the y-axis?
Intercept is 1 over
Just the x-axis for now. Or what's the y? What's the unit of the y-axis? 1 over 8. Or 1 over v, whatever you want to use there. Okay, so let's go back here real quick. For Michaelis-Menten, we seem to be, when we say plateau, it means that we're approaching some maximum rate, right? The Vmax. To get to that Vmax would require a huge amount of substrate concentration, essentially infinite, which isn't attainable in reality. So if we want to know exactly what the Vmax is, we can't use Michaelis-Menten. We can have a good idea, but we can't get an exact number. Lineweaver-Burke lets us get that exact number. That's the whole point. Because instead of having that curve, when we do a double reciprocal plot like this, we instead get a straight line, which is great. We love linear lines. Love them. Make things a lot easier. So in reality, this is the set of data that we're going to have. It's really going to look something like this. So those are the same points that we use to make the Michaelis-Menten. It's just we take the reciprocal of all of them and then put them in, and it happens to be linear. Now this doesn't reach the y-axis, and in some of the labs we talked about not extrapolating outside of like a standard curve. We go ahead and do that in this one, because we can get some useful information out of it. So even though there aren't points that go all the way to the y-axis, we can extrapolate the line out just to give us a pretty good idea about what the Vmax actually is. Okay, so Dan, what did you start to say about the y-intercept? Okay, so the y-intercept is 1 over Vmax. This, the y-intercept, remember, means when x equals 0, what does y equal? For x to be 0, remember x is 1 over substrate concentration. For this value to be 0, substrate concentration has to be infinity. That's what, when 1 over x equals infinity, x has to be, or equals 0, x has to be infinity. So we said we can't get to infinite substrate concentration here, but we can kind of assume infinite substrate concentration at that y-intercept, and then know what the Vmax is. Now, be really careful. If you're asked to solve for V, now this was the question that I wrote that Brent didn't go over, so I'll just tell you. Vmax is not the y-intercept. 1 over Vmax is the y-intercept. So if the y-intercept is -3, or sorry, +3, then the Vmax would be 1/3. So I feel like that wasn't that hard of a question. Change it. It's fine. Okay, so we can get Vmax. What's the other value that we can get from this? Better known as Km. Okay, what is Km in words? What does it tell you?
The substrate concentration where you have the maximum increase in rate of your reaction.
Not quite. The first half of that was good. The substrate concentration when...
You're at 1/2.
There you go, okay. So if we can estimate Vmax, then we can definitely estimate half Vmax. And we can go down to the x-axis, say Km is there. Since it's on an axis of substrate concentration, Km is a specific substrate concentration. It is the substrate concentration that gives you half Vmax. And it also tells you something about how much the enzyme likes the substrate. So I don't know if you remember this. There's like K1, K-1, and K2s. Km is a combination of those, doesn't matter what it is. But it just tells you how much the enzyme likes substrate and wants to convert to product. So we can get Km directly. I mean, with that, we have to still estimate Km because we have to estimate Vmax. But with this, we can extrapolate the line even more down to the x-intercept. And 1 minus 1 over Km is the x-intercept. So if the x-intercept is -2, Km is a half, whatever the unit of substrate concentration is. But you won't have to do that. But Lineweaver-Burke, you should be able to recognize the key. What's the key difference between that and enzyme enzyme concentration graph? Remember, if you're going to see these graphs, they will not be labeled whatsoever. It means you won't have the x-axis labeled, you won't have the y-axis labeled. So just off of the trend, We'll have to be able to recognize which graph, or which is the parameter being changed, what an enzyme concentration graph look like. It was linear, but what's the really important difference? They're both linear. Sorry?
It was all positive.
Okay, and it starts at 0, 0. Right? If there's no enzyme, there's no rate. That's what the origin means here. This one will never start at 0, 0. If it did, then the Vmax would be 0, and that doesn't make any sense. All right. What else? What time is it? Stay as long as you want. What else?
Can you just go over about back calculation for once you solve the concentration of an unknown riboflavin, can you do about calculate the mass of riboflavin?
All right, this is a standard curve between fluorescence and concentration of riboflavin. Okay, so those are standards, known concentrations. We measure the fluorescence, plug them into Excel. Excel gives us the equation of the line and the R-squared value. The equation of the line relates fluorescence to the amount or the concentration of the solution. We measure a unknown concentration of riboflavin. So one for your tablet, for example. And you get a little bit of the tablet, extract it with the sodium acetate buffer, dilute it a couple of times, measure the fluorescence. That's what we did there. So we measure the fluorescence of the unknown, and I'll just do random numbers, I guess. So let's say we get y equals, like, I don't know, 2x. We'll assume it goes through the origin. It doesn't matter what the numbers are, I guess. Okay, and then we get a fluorescence of our unknown of 0.3. And we'll say this is unit is nanograms per milliliter for riboflavin. Okay, how do I determine the concentration of the unknown from there? Solve for X. Okay, fluorescence is a signal. Your Y values, every experiment that you've done that's involved making a standard curve has had Y be signal and X be concentration. Okay, so please don't plug in your signal into X. All right, so 0.3 equals 2X. All right. This is the concentration of riboflavin in our really dilute solution. We want to know, the purpose of that lab was to see how much mass of riboflavin was in the tablet. Right, the manufacturer claims there's 20 milligrams in the tablet. What do the data say is the actual amount of riboflavin mass in the tablet? So I'll just do the series of dilutions that you did there. So we started with the tablet. You got the mass of the tablet, and then you measured out 7.5% of the tablet. So whatever those masses were, the only thing that's important is that you used 7.5%.
Why do we have to only use that again?
Sorry?
Why did we only?
Well, I mean, you could, if you know the masses of each of those, you can do it. Oh, yeah, okay, I get you. Yes, and then if we, so I guess the next thing we did was, I think we diluted it in a 200 milliliter volumetric flask. So we extracted this with like 150 milliliters of acetate buffer for 45 minutes, just let it sit. And then you put it in a volumetric flask and dilute the volumetric flask to volume. You didn't do that?
Well, we didn't,
Ours
we
was
used
the
150
That's why I
mils.
had it.
Okay.
But either way, the next one was to a 250, wasn't it?
So however much riboflavin is in this percentage of the tablet, we've now diluted it to 200 milliliters in a volumetric flask. And then at least the, some people in my class did this a little bit differently, but the manual called to take a milliliter of this, put it in a new volumetric flask, and dilute that to 250 milliliters. This is what we measured. So we had to dilute it quite a bit to get it to fall within the standard curve, right? That we need an unknown concentration to fall within the concentrations of our standards. Otherwise, this equation is worthless. Right? We can't assume that outside or below the standard curve, this trend stays the same. So we diluted it a lot, got to this concentration. Back calculation means get back to riboflavin here. So what do I do first? All I know is the concentration of this very dilute solution. So what should I do first? Yeah, so the first step is I'd like to know what the concentration is here. So how do I do that? Well, you're going to use the dilution formula. You need to be very careful about which numbers you use. What's C1? Well, we can do it either way. Let's say that this is our C1, that this concentration is our C1. What's V1?
250.
Why 250? Yeah, that's how much of it we have, right? All of the riboflavin that's in this solution is contained in those 250 milliliters, and we want to account for all of it. So really, if I multiply this concentration by 250 milliliters, that leaves me with mass of riboflavin. Right? Milliliters cancels. This leaves me with nanograms of riboflavin. So really, this equation up here says mass of riboflavin equals mass of riboflavin at different concentrations. That's what the dilution formula always says. Same amount of mass or moles at different concentrations. Okay. What is C2? We don't know, right? We don't know the concentration of this. That's what we like to find out. Here's where you're going to mess up. What is V2? It's 1. That's right. It's not 200, right? Because however much mass of riboflavin was in this solution came from 1 milliliter of this, right? This 1 milliliter that we took out, it did not come from all 200. It just came from that 1 milliliter of this solution that we took. So V2, 1 milliliter. $75.
It's 37.
Okay, so the concentration of riboflavin in this solution is 37.5 nanograms per milliliter.
Which that was like our unknown, right?
Well,
It was after the extraction before we.
yeah, so that means that however much mass of riboflavin was in this tablet, you then diluted it with this amount of sodium acetate buffer, but the mass of riboflavin is the same going from here to here, and that's the next step we're going to do, is if we know the concentration in the solution, we want to know the mass in this percentage of the tablet.
So that
And-
wasn't the percentage of the tablet. That's not the mass in the
No.
7.5% of the tablet.
No, not yet.
That's the amount, that's the mass per milliliter out of the 1 milliliter that you got from the 200 milliliter.
So we want to know, this number is on a 1 milliliter basis, and we can and should always make the assumption that this 200 milliliter solution is homogeneous, which means no matter which 1 milliliter we take out, it's the same as every other 1 milliliter. So if we know the concentration in this milliliter, that's the same as the concentration in this 200.
So you don't have to multiply it.
No, you don't multiply. You don't multiply by 200 to get the concentration of this. But we do still multiply by 200 because we want to know how much mass of riboflavin is in here. This is on a per 1 milliliter basis. If we multiply it by 200, then that tells us how much mass is in the whole thing. Right? It essentially puts it on a 200 milliliter basis, which is the entire solution.
So it's 7,500.
Thank you. Okay. So we now know how much mass is in here. All of the mass of riboflavin in here came from the tablet. So the mass of riboflavin in those must be the same. So this is the mass of riboflavin in the percentage of the overall tablet. So we are now here, mass of riboflavin. How do we go from this percentage to the entire tablet?
To multiply by 7.7.
I heard both answers. One of them's right. I think I heard both. So, should the mass of riboflavin be bigger or smaller in this?
Bigger.
Should be bigger. If I multiply by the percentage, don't write this down. It's going to be a smaller number, right? If you want to do a stoichiometric proof that you should divide, remember that this is amount of riboflavin in the portion of the tablet. And that ratio says that for every 1 nanogram of riboflavin, or however, for every 1 mass of riboflavin in the tablet, there are 0.075 mass, equivalent mass of riboflavin in the portion. Okay, remember this that 7,500 represents the portion. And if I want to cancel the portion of the tablet, then you're going to need to put that on the bottom. And now those cancel. And we get the million.
Yeah, the 100,000.
100,000.
Nanograms is an almost worthless unit to report mass in because a nanogram is such a teeny tiny bit that if you're talking about something on the scale of a tablet, you shouldn't say 100,000 nanograms. Instead, they say milligrams. So how many nanograms are in a milligram?
56.
Oops, hold on.
That's to a billion.
That's to a gram. 1 billion nanograms per gram. A million nanograms per gram. So if you divide this by 10 to the 6th, that'll get you milligrams, and will be the 0.1 milligrams of riboflavin. So back calculation means that you know how you got from one step to the next. You know the portions of each that you took. So you're just correcting for all of those changes.
So are you gonna give us, so is the question gonna look like giving us the values, and then us doing exactly just that, working
Yeah.
backwards, everything else will be
Yeah.
given. You want it in milligrams also, not in grams. That'll be the
Um,
final answer.
I don't know, I guess.
Okay.
Well, the unit will always be in the answer.
Okay.
I mean, in the sense of multiple choice, it'll be all in there, so you'll see what you should use. But do pay attention to the unit, it's important.
When you do like the dilution on experiment 1 for the protein,
Uh-huh.
and it asks why was it necessary to dilute the concentration, is that basically so that it will fall within your range that you're measuring so that you can make a plot and find the,
Yeah, a standard curve is only good in the range of concentrations from which it's made.
okay.
You cannot assume that it's still the same trend above or below the standard.
How did we account for that when determining the final concentration again? Do you remember?
Well, so when you had your protein solution,
Sorry, Sean, my brain is old. I don't remember that far back.
so yeah, this was the very first line.
Yeah.
So we had absorbance versus concentration of protein.
Mm-hmm.
And so then you would have had these points to make a trend line. And then you measured the absorbance of an unknown protein solution.
Mm-hmm.
And if that absorbance is higher or lower than this range, then you know you would need to dilute or concentrate the protein.
Okay,
If the absorbance is higher
then you need to
than
dilute.
your standards, it means that we need to decrease C,
Right.
right, to get this absorbance to fit within that range. So we would dilute it. So the way that you would account for it is when we're making the dilution, we would say, okay, let's do a 1-to-1 dilution, which means if we're using, if we want to make 10 milliliters
Mm-hmm.
of our new solution, we would take 5 milliliters
Mm-hmm. One and then
of our solution that we're diluting and 5 milliliters of whatever solvent we're diluting it with to make the 10 milliliters total. So this concentration will be half.
Can that be a 1 to 2?
It's
You can
different
interpret
people
it
call it
either
different
way,
things, yeah.
so
Yeah.
diluting it.
So then so the way that you would account for it is we would measure an absorbance, calculate the corresponding concentration, and then double it. Because we have the concentration in order to get it to fit into the curve. So whatever concentration we would solve for at the end is half as much as the original concentration.
That's only if it's a 1-to-1 solution, correct?
If you would write 1 to 2, then you can kind of see that you would need to double it. Because the aliquot factor is essentially 2.
Yeah, but I mean, you can have a 2 to 3 dilution too,
Right,
and then it's different. But but
You'd only double it if it's a 1-to-1 like you're
Yeah.
explaining. Okay,
Yeah.
but if it's like a 1 to 3 or a 2 to 3, then you'd have to
You'd multiply
You-
by
you
multiply
can-
it by 3.
you multiply it by hold on. Let's say your ratio is A to
Okay.
B. You would always multiply it by the other way. Because we're
Right,
when you're correcting for the dilution, you would do it like that.
Okay.
So in this case, it would be 1 plus 1
1
over
divided
1
by 1.
multiplied by 2. If it were our 2 to 3 example, then you would do 2 plus 3 over 2, you would multiply it by 5 halves.
Okay. Okay.
But yeah, the way you account for it is by, you know how much you diluted it by. So it's really just like the back calculation. It's really exactly the same idea. Knowing how much you diluted it by.
And then
Correct.
correct for that. Just mathematically, it wouldn't necessarily be anything other than that. Okay.
Really, it's just like slowing down and thinking what you did in reverse.
Yeah.
Kind of the best way to